Swayam Prabha. Digital India. Educated India.
Now you take any molecule, alright, put it in infrared spectroscope. Then you will see, you will record the spectra. Then you will see some, let's say 400 centimeter inverse to 3000 centimeter inverse. You will record some, you will see some peaks. No, it is not binding energy. Here there is nothing called binding energy. You will see some peaks. These peaks corresponds to the vibrational motions of the molecule. Alright. For example, maybe my number may not be right, but you can understand this. In this case, CH, when this interacts with the electromagnetic radiation, in infrared region, you will see a peak corresponding to 3400 centimeter inverse. These are all units. Alright, centimeter inverse is a unit which that spectra gives you. 3000 reciprocal centimeter units. Right. Now those who are working with this, they know that 3000 reciprocal centimeter, this much quantity corresponding to CH stretch. Right. So this frequency, how it comes? It comes because that particular bond, CH bond, behaves like a elastic spring. Therefore, the C is connected to H by a, that's what we are modeling. This is connected to, C is connected to H by a spring, constant K, but we are familiar with the spring constant. Therefore, CH, alright, that vibration frequency nu is equal to 1 by 2 pi into root of K by mu. This movement, alright, you are considering as a collective motion of the two masses M1 and M2 with the help of the reduced mass.
Sir, one more doubt is the number of ways a molecule can vibrate is related to the degree of freedom, right?
Obviously, I have not touched upon that. Suppose if I have n atoms, then 3n minus 6 degrees of freedom you will have. This is for a non-linear molecule. For linear molecule, you know that it is 3n, 1 will go 3n minus 5. So, in the case of water, let's take it as water. Then how many? We'll have 3 atoms. Therefore, number of degrees of freedom is 3n minus 6, 9 minus 6, 3. Alright. In this case, let's say you have like this, linear, some hypothetical. Then in this case, it is 3 into 3, 1, 2, 3, minus 5. Then you will have 3n minus. So this, you will understand this. I'm going more somewhere else. Therefore, this energy, all these are given in terms of some, this stretching is given in terms of the stretching energy, bending is in terms of a bending energy. Then I said this can be rotated, therefore there is a rotational energy. Not only that, I will have a collection of molecules, not one molecule. I will have an Avogadro number of molecules. Therefore, there is an interaction between two molecules, then the van der Waals interaction. They will also have electrostatic interactions. Alright. Therefore, all these parameters put together is called the force field parameters or force field expression. This energy is called as, this is the total energy of the molecule. Stretching energy, bending energy, torsion, van der Waals, electrostatic, all energy put together, it's called the total energy of the molecule in the classical sense. Tell me, somebody asked. Yes, sir. So your some molecule is here. You give energy, it will take the energy, then it will go to this. It will be excited. Alright, from ground state E0, it will go to the E1. But the energy tells you that it won't be in the excited state. When we want molecules to have energy, ground state as minimum as possible. Therefore, from here it will de-excitation takes place. The molecule will come to the zero. So this E1 minus E0 is given in the form of electromagnetic radiation, right? I am sure that you must have studied this in atomic physics, right? Or at least the early part of your quantum mechanics, some aspects of quantum mechanics dealt in your schools. Definitely people would have Sommerfeld model, right? Various atomic models, when you see that, these are all taught. So it wanted to come back to this. So this is the energy. Yes. Huh? E cross. I am not to tell you. It's all the cross terms. Right? Let's not worry about cross term here. Huh?
So torsion energy is the
Energy due to rotation. Torsion energy or rotational energy is the energy due to the rotation. Yes.
So in the system, linear system, for degrees of freedom, we consider system. So in that, why don't we consider rotation?
In that, why don't we?
For degrees of freedom, you consider rotation.
I will come back to that point. Why we are not? Let me finish and explain. All right. Now this is the you have a typical example of a molecule which is vibrating. Right? Yet this particular group is only vibrating. Right? I am just showing, but all the groups will be vibrating. Right? So this is the stretching. So it elongates and compresses, elongates and compresses. Therefore, there is a energy involved. That energy involved is approximated as half k x square. Right? Half k x square, which I have written because you consider them as a spring. I have another one. The next is right. Next is a bending. Let's not. Yeah. So I have some molecule which is bending like this. Therefore, there is an angle. This angle also bending is taking place. Therefore, this is theta. Again, this can be approximated. This length is approximated as half k x square. Angle is also approximated as half k theta minus theta. Original angle is at theta 0. At any instant it is theta. Therefore, it is theta minus theta 0 is the angle. Alright. Next is that's what there are several terms one can add. I don't want to add all this. Then another very important is the rotation. So this is the rotation of a CH3 group. So about this bond, the group is rotated. Therefore, it is rotating with respect to angle omega. Therefore, it is a very, very important. There is an energy penalty for that. That energy is this energy Vn. Right? It is a barrier rotation. I am sure you must have heard this in your course. Alright. Let us, yeah, let's take this example. I rotate. Now you see from CC bond, then you will get two kinds of structure. Right? One is staggered, another is eclipsed. So that arises mainly because of the rotation. That's what it is happening here. It is rotated like that. Alright. So this also will have energy. Therefore, this energy due to rotation, there is an energy due to rotation. That energy is called barrier to rotational. That is, I can plot this as a function of, this is E as a function of omega, 90, 180 and so on, alright, like this. So this energy, right, when I rotate, I am not considering the other aspect, so maybe you can have the talks, there is nothing wrong with it. So this is the maxima and this is the minimum in terms of the energy. So this is your eclipsed and this is your staggered. Staggered will be lower in energy when compared to this. So the energy required to rotate this is called the barrier to rotation. This energy is Vn. So that Vn is written here. Energy due to the rotation, right, that you call it as this energy. Next is van der Waals interactions. We have seen this in physics.
Sir?
Yeah.
Sir, so could you explain what barrier to rotation is again?
Yeah. Suppose if this barrier is 20 kilocalorie per mole, so I can't supply that much energy to rotate it. If the energy is larger, right, it may not happen. You understand that? That's a barrier, right? Height. Now this van der Waals interaction is, you are all already familiar, right? PV equal to RT. What are the assumptions? Anything else? Laws of gas. What are the assumptions? What is ideal gas behavior? There is no interatomic or intermolecular. Right. Anything else? So why? So therefore, no. The basic assumption is that there is no interaction between two molecules or two atoms. Alright, but that is wrong. Alright, so we changed it. Similarly, we said that there is no size. Alright, but no. Suppose I take a volume, I put one molecule, then next molecule. Then if I come, when I put the first molecule, the available volume for the second molecule increases or decreases or remains the same. Decreases. It decreases by a term called B. Alright. Therefore, this equation is modified. Alright. How we modify? We modify this as P plus A by B square into V minus B equal to RT. What is this interaction? This arises mainly because of the intermolecular interaction. Alright. So, this is the volume correction. Alright. This is called the co-volume. Yes or no? Yeah. This equation is called van der Waals equation. You are all familiar, right? So this is the van der Waals interaction. Where you will see between two helium atom, you will see between two neon atom, right? You see between two methane, you will see this between two benzene. Alright, this interaction is called a van der Waals interactions. That is, as such, they don't have any dipole moment. Right? How many of you are familiar with the word dipole? Right? It is a charge into distance. Right? So they don't have any dipole. All right? Zero. But when the molecule with the zero moment sees another molecule with that, then there is an induced dipole moment. This molecule induces onto that. Right? So this is an induced dipole interactions. This is called the van der Waals interaction. This is modeled by variety of classical potentials. Alright? They are called, the familiar one are called 612 potential. See, originally people thought that helium is, all these helium neon are monoatomic, but they are not, right? Right. So 612 potential. What is the 612 potential? This will have a attraction component and a repulsion component. That's what it is. When the two atoms comes very, very close, their electron density are overlapping, pushed, alright, then no, there is a repulsion. But at a reasonably distance in which this negative positive kind of an interaction, you can think of it as a model, alright, this is called the attraction. Therefore, the motion of electrons temporarily create a induced dipole. That's what it is. Originally they don't have any dipole. The motion of the electron creates a dipole here. Now you have a charge separation. This creates a dipole moment. This induced dipole-dipole interaction, we call it as the van der Waals interaction or van der Waals energy. At a very small distance it is repulsive. Overlap of the electron cloud of one atom with respect to the other. At intermediate distance here, there is a slight attraction. This is due to the motion of the electrons. At a large distance, there is no interaction. Therefore, this also modeled in molecules.
Sir?
And yes, sir.
Sir? Sir, could you please explain that 612 potential once again?
I will come back.
Okay, sir. Sir, and one more doubt. In the van der Waals equation, could you please explain what that A by V square and V minus B, those parts are?
Yeah, A by V square comes from the see, therefore, the force experienced is taken into consideration. Alright. Therefore, you have a P plus A by V square. And B is the volume part. I have a total volume V. Now another molecule is coming. Alright. The volume available for the next molecule will be less. Third molecule less, fourth molecule, and therefore the net volume available because of the size consideration, it is less. This comes because of the force. We assumed that there is no interaction. If there is no interaction, there is no potential energy, there is no force. Pressure is nothing but force, you know that, right? Therefore, there is a change in the pressure. That is given by this A by V square and V minus V.
Thank you, sir.
Right. And you can later work a lot of other details. Alright. In fact, you can calculate dP by dV as well as d square P by dV square, setting it to 0. Then you can get the all critical constants. Alright. Have you done this? PC, VC, TC. Do you remember that? No. Maybe critical constants. PC, VC, TC, RTC by PC, VC equal to 8 by 3. No. Definitely will be doing this in your physics. If I start doing that, then I will deviate from my thought. Right. So this is the van der Waals. I will come back. This is called the 612 potential. If you look at this equation, right, we can note that I will explain on the board. Alright, I take two atoms B. Alright. Now I plot this, right? Now when I compress this beyond a particular point, then this is the repulsive portion. Alright, this is 0 and this is the minimum on the potential energy surface. Alright, and when the distance is very small, then the electron cloud of this will repel immediately. Therefore, this side will be very steep, and From here it starts getting attraction. These two are attraction part. And this is the minimum on the, it crosses negative, it crosses 0, it is negative here. This is the minimum on the potential energy surface. And since when the distance is small, it should repel immediately, it is modeled by 12, r to the power 12. When the attraction portion is modeled by r to the power 6, that is the induced dipole. Charge varies as 1 over r. Charge, that the potential due to charges, point charges, is q1, q2 divided by r. It varies as 1 over r. Now the product of dipole varies as 1 over r to the power 3. Induced dipole, in this case, it varies as r to the power 6. Alright, the repulsion is modeled as r to the power 12. This is varied as r to the power minus 6. That is the origin of this. So I can, there are several forms. I am not going to describe you all those. Then I can have an electrostatic energy. Electrostatic energy I can model simply a point charge q1, another point charge q2, q1, q2 divided by r. So I model this as q1, q2 by r. Yes, sir.
Excuse me, sir. Sir, the graph that you drew, I thought it was only true for nuclear forces. So, is it also true for interatomic and intermolecular forces?
Yes.
So, they can also become both repulsive and attractive. They are not only attractive, like beyond a certain point of the distance between them.
They are only if the molecule is formed, then they will be like this. If the two interaction is stabilizing the molecule, you will have a minima energy, which is below negative, below 0, negative. Repulsive means the energy is positive. This is the minimum energy. This limit is called dissociation limit. This is the formation of bond. Let's say you have a AB bond is formed here. Here this becomes A plus B. It becomes separate. Initially I have a AB, I put them together, they form a bond. If it is dissociating, it goes like A plus B, because you put A plus B to form AB. When AB is at large distance, when the distance becomes very, very large, there is no interaction between A and B. In that case, then it becomes a plus B. So this is called dissociated limit. This is the bonding, this is the repulsion. When the electron clouds are overlapping beyond, no, you can't push, it will immediately. So how many people I can put in this chair? I can put 3, I can put 4, I can, then when I put 6th one, she will repel. Got the point? Right.
Thank you, sir.
So I can do the point charge and so on. So you can see that that's what I said. Alright, this and all you can ignore. Alright. So I can think of this as a spring. I already told you this. I can think that triatom as a spring, considering of spring. 4 atom also like that. So I can use the 612 potential to model and so on. So when you look at the molecules, there are certain time frame is very, very important. I already told you. So the bond stretching, I already told you, it takes place in femtosecond. If with reference to the protein, certain domains will move very fast, 100 femtosecond. Biology, you have a lot of water molecules, therefore they reorient in 4 picosecond. These are several orders of magnitude of motions and molecules are very, very important. We look at that. Alright. Basically what we do is, we do the dynamics. Because I already told you that I am not interested in static picture, I need to know about the time evolution, therefore dynamics is very important. Therefore, what we'll do is, why dynamics, I already told you, it is important to predict the structure, understand the interaction, right? These are all very, very important. Not only that, all these biological experiment or chemical experiments, any experiment that you do, all these are happening in certain, if you look at a physics experiment, some solid state materials, it is happening in a solid state conditions, or if you do look at any chemical reactions, they are happening in some solvent conditions. Biological molecules, they all behave in water condition, water aqueous solutions and so on. Therefore, we need to model the solvation phenomena. So, what we started from the structure of the molecule. Now, also we looked at the how two molecules are interacting, that also you model. And then now we want to look at the realistic situation, whether how these are interacting in a gas phase or in a solvent medium or in solid phase and so on. Therefore, the environment is important. Therefore, the solvent, how are you taking into consideration? What I will do is, I construct a box, alright, yes, 3-dimensional, and then put water molecule here. I have fill this box. Mathematically, again this is done mathematically. I can put this water molecule here, right, and then put the molecule inside. Therefore, no, I simulate the experimental conditions, right. Therefore, how do you do that? There are several water models are developed, right. That's the very, very important contribution from India, right. Professor J. Chandrasekhar, right, PhD from IIT Madras, chemistry department, right. He has done this work, water molecule, right. It's, I think it is cited 1 lakh or 50,000 or even more than that. I don't remember exactly. These models are called the water models, right. It's called the TIP 3P. That is, water is modeled as 3 charges. 4P means model as 4-point charges. 5P means it is modeled as 5-point charges. Because if you look at the water molecule, alright, this will have a charge Q, oxygen, QH. Then you will have 2 lone pairs. Yes or no? How many of you are familiar with the lone pair? Very good. Therefore, this also will have a charge, right? That is the 5 charge 0, 1, 2, 3, 4, 5. So, it is modeled as point charges, 5 charges. Therefore, it is called 5P. Therefore, water can be modeled as charges. Therefore, you can create a water box, right? Then what we have to do? We know all these things now. We are all familiar with this equation. I started up this equation. I will take the molecule, put it in water medium, right, and then I simulate the molecule. But before that, you need to do a lot of other things. I am not going to explain all those things here. So, this is a typical example. You will see that in a water medium, this is what a dynamics. This is a simple protein, azurin, alright, it is a copper protein, alright, it is so it is making very, very important motions, right. You can, from this you can understand that how this sheet molecules are behaving, how this helix behaving, how this random coil is behaving and so on with respect to the time. Like these details you can get it from the molecular dynamics simulation, right. I thought that I will introduce this concept to you so that you can understand the motions and proteins. One important question that I have addressed kindly switch off. Give me some time. Any questions?
Sir,
Yeah.
sir, in the beginning of the class, you gave a graph that represents the order of.
Without mic, you can speak.
Sir, you gave a graph regarding the order of magnitude of various there was this thing called Monte Carlo in that. What's that?
Yeah, this is Monte Carlo. In fact, Professor Balakrishnan is very good in that, and anyway, I'm not getting the correct one, which I wanted to spend some time with you people. Right. I will come back to that. So this Monte Carlo is like this. For example, I have some, now I calculate, now you know the total energy of the molecule is stretching, bending, torsion, you agree with me, right? Plus van der Waals plus electrostatic. So this is the total energy of the molecule. Now for a given molecule, I calculate this energy, all this energy, and then I will change the distance. Then I calculate this probability. What happens to this quantity? E power E by RT. If it is within certain range, you accept the moment. If it is not there, then you reject the moment. This is called Monte Carlo. Alright. That is the algorithm we use quite often. Next room, somebody is there. His name is Suraj. He is authority on. He is also working on Monte Carlo, quantum Monte Carlo. We call.
Sir,
Yes, sir.
so you had told that for a stable molecule itself, there are so many components that add to the total energy. How will it vary with an ion?
Tell me.
For a stable molecule, if there are so many components for its energy, how would which of those would vary for an ion?
No, all will change for the ion. Everything will change. All properties will change because all these are a reference to a particular ground state. You make it as positive ion, you make it as a negative ion, all these properties will change. With reference to for the given molecule, the ground state energy is minima. How do you characterize the minima? We are familiar with the maxima minima, that is y is equal to, let's say y is equal to f of x. Let y equal to f of x. Then dy by dx, that is f prime of x. For maxima, for extremum, right? Maximum or minimum, this quantity is 0. Alright, yes, same thing. Alright, for the energy of the molecule, E is a function of so many R. So you will have a Ri, so many theta, right? So many omega. Therefore, with reference to all this, dou E by dou Ri is equal to 0, dou E by dou theta I equal to 0, dou E by dou omega I, for all this is equal to 0. So this gives me the condition that whether the molecule is on the minima or maxima. Then we have to characterize. How do you characterize? You have to calculate the second order derivative, d square y by dx square. If it is positive, minimum. Second order derivative is negative, it is maximum. Because this is intimately, this quantity is intimately related to the force constant. Because you are familiar with this. I will go beyond what I wanted to do. It is root of k by mu. The second order derivative is equal to force constant. You take it from me, I am not going to describe. It is force constant. So if this is positive, then only you will have a real frequency. If this quantity is negative, then you will have a imaginary. Imaginary you can observe in the experiment. Therefore, the molecule cannot be in the maxima, it can be only in the minimum of the potential energy surface. Right. Right. So what I will do here is, from here I will straight away go to some application. How do you do this? I am not going to tell you all. I am going to take only the few results. Yeah. Yeah. This is a very interesting exercise. Don't look at all these details. Now I have a large protein. Alright, this is a very large protein. Now when you look at the structure of the protein, you can characterize them in terms of that primary structure. Primary structure is called sequence. Then secondary structure, that is, I have shown you some helical, sheet, all those things. Then quaternary structure and tertiary structure and so on, various levels of structure. Leave that. Now when you look at the structure of the protein, three-dimensional structure of the protein, they will have pockets or they will have a cavities. Alright, now I want to develop some inhibitor. This molecule has some action. This protein has some action, and this site, the site which I have shown here, where I have filled with some molecule, this site is the active site or business site. Now if I block this site, the activity of this enzyme is blocked, alright, from biology point of view. So it is by interacting with this, I inhibit the biological activity of this particular molecule. Now how do I put these two together? There is a technique called docking. Right. Now I have seen, I know how to calculate the energy of the molecule. Alright. Now what I can do here is, I want to put two molecules together. There is one large molecule. So this large molecule is protein. I can look at where these molecules can bind. Small molecules can bind. Therefore, protein, small molecule interaction is very important. So, this protein this is a large molecule. This will have 3 degrees of freedom. This can rotate x direction, y direction, z direction, so on. And I have a small molecule. This will also have these kinds of properties. So, I have this is 3 plus 3, 6-dimensional fitting. So, what I am going to do here, I am going to fit this small molecule into the cavities of this particular protein. By this process, I am going to inhibit the biological activity, right? That is the exercise. This is called molecular docking. What I will do, I calculate the energy of this molecule. I calculate energy of the small molecule. What is the difference in the energy? That is energy of the complex minus energy of the individual units. I have 2 units, this A and B. I can calculate this energy. Therefore, this is the interaction energy. This process is called docking. Somebody said binding. Now this binding comes. I put 2 molecules together, then I get a binding. Alright, this is the binding mechanism. This is called docking. So, docking can be scored. The one which has the highest energy called as the first one with 1, then the lowest molecule will have a, because if we explore the chemical spaces, I will have a lakhs and lakhs of small molecules with a varying biological activity. So, what I want to do is I want to interact all those lakhs and lakhs of molecules with a protein. If you want to do that, can you do experiment? Very costly, time consuming, alright, impossible to do this. In that case, the molecular modeling comes handy. It is used to screen large databases. Somebody said, I want to do the data mining, data science, right? The data science is applied here at this moment, right, on this kind of thing. What we did here is, I am not going to explain everything. The last 3-4 years, the active area is this. This area, SARS-CoV-2. At that time, we don't have any medicine, right? When this pandemic came, what to do, we are not familiar, right? So, Gilead is a company, right? What they have done previously, they used molecular modeling to repurpose already existing antiviral compounds. At that time, probably you all must have heard about something called remdesivir. How many of you heard about antiviral called remdesivir? Anybody else? It's a very, very important at that time. People have been talking about, if you are given with the remdesivir, viral load will decrease. That's what people have been working. Therefore, Gilead has found already that because of the molecular modeling, they found that this is a very good antiviral. In fact, there is different opinion about remdesivir, the efficacy of the remdesivir. But I have personally seen that in very close case where I have not taken, but I also suffered, but I have not taken. One of my very close student, right, he has to take this remdesivir. There is no other, otherwise he will die. Right, in that situation, they have given him remdesivir. That really decrease the viral load in the body. All right, there are different opinions, but I have personally seen. After effects, I don't know. At that time, people are trying to develop new molecules, repurpose molecule. All right, these are all some important viral proteins. All right, 3CL Pro, it's called main protease, PL Pro, spike protein. RNA dependent RNA polymerase RDRP, NSP9, it is called non-structural protein 9. Alright, there are several proteins which are very, very important. Another is helicase, endoribonuclease, ACE2, it's a human one, TMPRS2 human one, JAK2, these are all human one. These are some protein which are very proteins and enzymes are very, very important part of the SARS-CoV-2. People have been trying to put all these molecules together, right, small molecules with these components, and then try to develop a particular compound which can be a better inhibitor of these activators. That's what people have been trying. Alright. So what we did is we took the database, alright, and then interacted all the laxin compounds with various proteins of the virus, and then we found that there are some molecules, right, these are all the top 10 molecules which can go through with the 3CL probe. Right, these are all the lead information. You can further take it up and then work on it to develop a drug molecules. Alright, so that's the idea here. So in the last 1 hour and 40 minutes, what I was giving you is I was giving you the principles, physics behind the molecular modeling, alright, and then how this is used to get some very, very interesting application, right, or idea on antiviral developments, alright, especially the very recent one, it's called the pandemic. In fact, after this, we also ventured, alright, at the time, many would have taken something called the Kabasura Kudinir. அது யாராவது குடிச்சா குடிக்கலையா? எல்லாரும் சாப்பிட்டிருப்போம் இல்லையா? அந்த கபசர குடிநீருக்குள்ள என்ன இருக்குன்னு யாருக்கும் தெரியாது, ரைட்? ஸோ அதில் என்னென்ன இன்கிரீடியன்ட் இருக்கு, என்னென்ன குட்டி குட்டி மாலிகுல் இருக்கு, ஏன்னா தீஸ் ஆர் ஆல் plant products will have variety of phytochemicals, right, organic molecules they will have, right, how these small molecules, how these organic molecules are constituents of this Kabasara Kudineer interacts with these viral protein, alright, that's a very, very important exercise. In fact, we have done that during the pandemic. Then another one important one, what we have done here is, there are Adadoda Vasika, alright, those who have done botany, they know what is Adadoda Vasika, right, we also familiar at home, unga party oda party, right, it's like grape water advertisement, right, they would have given this Adadoda Kashayam to all of us, right. How many of you are familiar with Adadoda Kashayam? Right, there is, you know, if you go to IMCOPS, they sell you Adadoda Manapagu, right, it looks like a, that Kasapu won't be there, it looks like more of jaggery, alright, that Adadoda Manapagu, alright, it is very, very important, in fact, I used it. So that, you know, they give you. This Adadoda Manapabu has, quite a lot of antiviral properties. In fact, we explored all the antiviral properties of this Adadoda Vasika, alright. There are many things one can do with the molecular modeling. In fact, not only we do this molecular modeling, we also collaborate with the experimental biologists, right? Because, you know, whatever that you get, this may not be the ultimate. You need to prove this with experiment. Therefore, we identify some compounds and then from this they select the best one, then explore the experimental side, because this is only a lead hit. We call hit molecule, lead molecule. But after that, now we have to explore what is toxicity. We have to experimentally determine what is the biological activity, toxicity, and not only that, this affects only one protein, but whether while taking inside, it will also affect the side effects. So how do you look at the side effects, toxicity, ADME property, and so on? No, one can model as well as experimentally determine. So with this, I stop here. All right. I gave a flavor of, not complete, I gave a flavor of what is meant by molecular modeling, and then how this can be applied to understand the interaction between protein and ligand molecules, eventually which can get into what you call the drug discovery process. I thought that I will share something very, very interesting one. Other than this, the slide is missing. Very recently I spoke somewhere, but I'm not getting it. Okay, but I will show this and stop here. Yeah, this is the, basically you do the dynamics. Can you see this picture? Let me stop. Can you see this picture? Yeah. So this is the very early work of mine. Right. This protein is called collagen. COLLAGEN. It is the skin protein. How many of you are familiar with the skin protein? Who discovered the structure of the collagen? DNA. Huh? Right. எவ்வளோ வெக்கமான விஷயம் தெரியுமா இது? ரைட், நம்ம ஒரு இந்தியாவில் இருக்கிற ஒரு கான்ட்ரிபியூஷனை மறந்துட்டோம். என்ன, நமக்கு ரிச் அண்ட் கிரிக்கு அடுத்த கண்ட்ரி, ரைட், நம்ம வீட்டுக்குள்ளே என்ன இருக்குது அப்படிங்கிறது யாருக்குமே தெரியாது. ரைட், வாங்க அங்கே பக்கத்து வீட்டில் என்ன இருக்குது அப்படின்னு, அவங்க வீட்டில் என்ன டிவி இருக்குது, உங்கள் வீட்டில் என்ன டிவி இருக்குன்னு ஒன்றும் தெரியாது. பக்கத்து வீட்டில் இந்த டிவி வாங்கியிருக்காங்கன்னு தான் தெரியும் நமக்கு. Right, it's like that. No, our attitude is like this. We know rich and crick. We know Watson and Rich or Watson and Crick, but we don't know who is G.N. Ramachandran. I thought that I will show that with end the topic. Right, it's a very very important protein. Right, இந்த பொண்ணு எவ்வளோ அழகா இருக்கா, இந்த பையன் எவ்வளோ அழகா இருக்கான். ரைட், இந்த பையன் ரொம்ப ஹேண்ட்ஸமா இருக்கான். ரைட், இதெல்லாம் எப்படி, எதனால? Skin protein. The major part of the skin is collagen. அவன் எட்டி பார்க்குறாங்க, யார் அந்த அழகு பொண்ணு அப்படின்னு. ரைட், உன்னோட நாம கூட நல்லா இருக்கு. ரைட், so this is the major part of this protein is called skin protein. அதோட ஸ்ட்ரக்சருக்கு பேர் வந்து triple helical structure. I thought I will share this with you. Maybe if time permits, I will come back to you for a few minutes in the end of this particular program and show you what is the work of Ramachandran. So at that time, he is a former student of Raman, Sir C.V. Raman. He was asked to develop the Madras University Physics Department. Then he wanted to work on some problem, research problem. Then he was asked by the then people to work on the collagen. It is called the very very important protein, skin protein, because at that time it is very important. It's a fibrous protein, right, and if you look at the X-ray diffraction pattern, nothing is visible. So he really developed the idea of what is called triple helix. At that time, there is no information about triple helix. 1955, 1954, right? So there is nothing about the double helix. Those who want to do biology, யார் நிறைய பேர் சொன்னீங்க biology படிக்க போறோம் அப்படின்னு சொன்னீங்க. அவங்கெல்லாம் ராமச்சந்திரனோட ஒர்க் தெரிஞ்சிருக்கணும். Right? He is the father of biophysics and molecular biology and structural biology in the country. Right? He started the first X-ray diffraction of proteins, right, in the country, and Professor Vijayan is the first crystallographer in the country, trained crystallographer in the country. Right? So he took this particular problem and solved this. But there are a lot of issues regarding the hydrogen bonding pattern. Right? In fact, I have not spoken about the hydrogen bonding pattern. We can talk about hydrogen bonding also. It's a very important one in the case of a drug discovery. Hydrogen bonding, how two molecules are hydrogen bonded. Right? How they are hydrogen bonded? Huh? Phi and psi angles. She is telling something closer to Ramachandran, but not phi and psi. Ramachandran also made a contribution to phi and psi. Right? The rotation of a protein. Right? Hydrogen bonding is different. Hydrogen bonding is this. Suppose I have a water molecule. I have one OH, right, and it is going to interact with another OH like this. Right? This kind of a bonding you call it as the hydrogen bonding. This is also sort of a non-covalent interaction, higher van der Waals interaction, but it is a special topic. Right? In the case of a non-covalent interaction, it is a very special interaction wherein this will have a delta plus minus and these two interact. This is the hydrogen bonding interaction, and this distance is a typical distances of the order of unit. Alright. The idea here is there are several criteria why this has to be hydrogen bonded, because in the case of a protein and ligand, right, in the case of protein and ligand, right, the ligand can also make a hydrogen bonding interaction with the protein molecule in addition to the non-covalent interaction. There is something called Lipinski rule. Rule of 5. Alright, it should have so many number of hydrogen bonding interaction and so on. These are all the very important one. I stop here. So molecular modeling is a technique which is very useful to understand the interaction between two molecules, and in biology it is used to understand the interaction between protein and ligand molecules, DNA and ligand molecules, and protein and DNA and so on, which eventually led to various other processing. Alright, with this I stop here. Thank you for patient hearing. I will, if time permits, maybe I will come back to you. Right, if somebody is interested to do some project, the project which I suggest here is more or less similar to this. We can select some problem which is related to the protein structure function. You can look for some protein, come back to me, how the protein structure evolves in time. Alright, how do you predict some properties of the protein? Alright, basically the interaction, you can take some small molecule and we can interact with them and so on. So these are all the possibilities. So the project may be, if I ask to give projects, I will be giving projects only on drug discovery. Alright, maybe antiviral development for the SARS-CoV-2 and so on. Right. With this I stop here. Thank you for patient hearing. Alright, we'll come back. Thank you.